I turned my sound off so I don't get the little trigger thing. Okay, recursion. First of all, what is recursion? Let's see if we're awake today, since we all just answered this. Go ahead.
Is it a process that loops itself without any actual loops in it?
Okay, I mean, that's, I guess, a weird but somehow accurate description. Yeah, so it's a function that calls itself, right? So we can sort of kind of write loops without a loop, where the function actually makes a call to itself over and over and over again. All right, we used this a lot last class, didn't we? We wrote the code that does all the splitting of our merge sort. We have we did factorial recursively. All right, so now what's good about recursion? If recursion has a benefit, what's a common benefit of recursion? This all was on the same slide, same one slide. Go ahead.
It's an elegant solution.
Yeah, usually it gives us a short solution, an elegant solution. Remember when we wrote factorial last time? The version of factorial that we wrote recursively was just 2 lines of code. Just kind of like, oh, that seems magical, but it works, right? So it's obvious, it's usually an elegant or a short solution, something like that. What's bad about it?
Takes its own memory.
A lot of memory. A lot of memory. Because every single time we need to put a call to a function on hold, we have to remember the current state of that function. You know, we have to remember that the current value of n was 4. And the next time we had to remember that the current value of n is 3. And it goes deeper than just remembering about a current value of one variable. Because some functions have a whole lot more than one variable, right? So there has to be this generic data structure that exists in our programming languages that has to decide, I'm going to represent a procedure or a function like this. This giant data structure that keeps track of as much stuff as we might ever have inside of a procedure. And we're going to throw that whole thing on top of the stack. Then we're going to throw another one on top of the stack, so on and so forth. All right, so it can get very expensive from a memory perspective. That doesn't mean don't use recursion. It just means recursion is probably a poor idea in situations where you're going to do something many times. If you know you need to do something that many times, you probably could do it iteratively. All right? But recursion usually gives us kind of an elegant solution where, for instance, let's take merge sort, where we're saying, is this the one list? Is begin the same thing as end? If yes, we're done. We're sorted. If not, call merge sort on the left, call merge sort on the right. Why? Because we want to sort the left and the right. And how do we sort stuff? We call merge sort on it. Kind of makes some elegant sense as soon as we get our brain out of the infinite loop, right? Okay. Now I did tell you all that you're going to struggle with recursion for a while. Okay. Now the homework assignment didn't have any recursion in it though. You wrote recursion for the merge step, you wrote it wrong. You shouldn't have had to do recursion for the merge step. We wrote all the recursive calls last time. Yeah, I mean, so the merge sort has recursion in it, heavily. Merge sort has 2 recursive calls, but we wrote the recursive calls. So all you had to do for your homework, all you had to do, was that merge step. All right? And what was that merge step? Well, as I recommended to some of you in the general chat for the class who are struggling with this, let's look at our merge step. Maybe let's say we came back to our top level so we can see this a little bit. And let's go ahead and unsort these. I'm actually going to move the indexes below because that makes more sense to me. So we're going to say 1, 7, 8, 2, 3, 4. All right. So after our final calls to merge sort have returned, all right, and we're ready to do our final merge step. And we're going to do this merge step several times. Because remember, each time through our merge sort, our goal is to get the little sublist, the part of the world that we're currently interested in, the part of the world that goes from begin to end, as we're passing those values around, we want that to be sorted. All right, we're relying on that so that when we get back up to after the original 2 calls to merge sort, we're set with something that looks kind of like this. That is, where the left half is sorted in and of itself. 1, 7, 8 is in order. And the right half is sorted in and of itself. 2, 3, 4 is in order. But this whole thing isn't necessarily in order. Make sense? This is where we perform our merge step. So every single time we have a list that's ordered where the left half is ordered within itself and the right half is ordered within itself, we have to do a merge to bring that entire sublist in order. So we're going to do our example here on the big list just so we have enough moves to kind of to realize the algorithm. All right, so when we get to here, we have a left begin. So we called it, I think we called it left begin, didn't we? And we called it, we had a left begin, left end. And then a right begin, right end. So those match our variable names. All right, so in this particular case, left begin would be equal to 0, left end would be equal to 2, right begin would be equal to 3, right end would be equal to 5. Right? The beginning of our left list is at bucket 0, the end of our left list is at bucket 2, the begin of our right list is at bucket 3, the end of our right list is at bucket 5. So those are our two sublists. And we know that the right half is in order and the left half is in order. Presuming that all the merges we did prior to this were written correctly. All right, merge is just a single algorithm. We just need to perform it many times on small lists. So we're going to assume this is our final merge step, where we're doing it on all of our data back at the very top, where we have the left half sorted, the right half sorted. Now we need to merge them back together. Okay, so step 1 for our merge step. Let's give ourselves, let's write our little algorithm here. And you should always start by doing something like this when you're working in your homework. Draw pictures, try to write your algorithms in English. All right, so first thing we need is we need a place for our ultimate list to live, as we're deciding what's the smallest value, what's the next smallest value, so on and so forth. So we're going to need a new array big enough to house everything from left begin all the way up to right end. So in this case, this is 6 elements, right? Or right end minus left begin plus 1. That's the number of total elements we need in our temporary array. So create temp array of size right end minus left begin plus 1. All right, so that's the first thing we'll have to do. That'll give us a place to put our final answers. So we'll just copy this, bring it up here. We'll move these guys back together, and we'll empty it out for right now. Okay, so maybe we call this guy temp. All right, so that's temp, and temp has enough buckets in it to hold all the values from the 2 lists that we're about to merge. Make sense? All right, so that's what we did first. We haven't done any merging yet. We just created a place to do our merging. Now, we need to ask temp.length questions. That is, for every bucket in here, we're going to be placing a value. Which value we're going to be placing? We're going to be placing the smallest value between where we're currently looking here and where we're currently looking here. So that means I need 2 variables to keep track of where I'm looking in each of these places. All right, so I'm going to go ahead and we're going to create, let's call this guy curleft. Maybe curleft starts off at 0 or starts off at left begin. And then we're going to have a curright. And he's going to start off at right begin, which is 3. Okay? So these questions are going to involve, well, before we ask those questions, let's say, create vars to point to the beginning of each sublist. That's what cur left and cur right are. All right, cur left, cur right. Cur left is going to point to the very beginning of this sublist. That is the position of the smallest value in this left sublist. Cur right will point to the beginning of this sublist. That is the position of the smallest value in this sublist. And then we need to ask this many questions so that we can place each of these 6 values in their appropriate place in these 6 values. All right? What's the question we're going to ask? We're going to ask which should come first? The element from the left sublist at position cur left, or the element from the right sublist at position cur right? Which of those should come first? All right. Now we have to understand that there could be the situation where cur left is out of bounds or cur right is out of bounds. What does it mean for cur left to be out of bounds? When is cur left not a legal position in the left sublist? When what's true? Go ahead.
When it's greater than left end.
When it's greater than left end. All right. So we need to ask temp.length questions. Some things to keep in mind is cur left is illegal if it is greater than left end. When is cur right illegal? Greater than right end? So cur left and cur right are illegal positions if they are greater than left end or right end, respectively. If both of them are legal, then we're just going to ask the question, well, if one of them is illegal, then the other one wins by default, right? If the guy doesn't show up for the fight, he doesn't get any consideration, all right? Otherwise, if they're both legal, that is, neither of them are beyond the end of their sublist, then we're going to ask the question, which value is smaller? The value at position cur left or the value at position cur right? Okay, that makes sense? So if both are legal, which should come first? Cur left or cur, well, whatever. Let's just say which should come first. Good enough. So we will place, regardless of which of those things happen, we're going to, let's do this, place the winner of the question in the next open spot in temp. Okay? Which means we're probably going to have to keep track of our current position in temp. So let's go ahead and give ourselves a temp pause. And this guy would start off at 0. That is, the first value we're going to place in temp pause is going to be at bucket 0, then it'll be a bucket 1, then it'll be a bucket 2, then it'll be a bucket 3, bucket 4. So temp pause tells us where's the next place we put our winner inside of temp. So we're going to be determining our winner from our sublists and then placing a copy of that winner inside of temp. So in this particular case, we're going to ask the question, which is smaller? Whatever is that position cur left, so a 1, or a 2, which is the smaller of those two values? 1. So we'll place a 1 at position temp pause, increment temp pause, increment cur left, because left was the winner. Which should come first, a 7 or a 2? The 2, place it at position temp pause, increment temp pause, increment cur right, because that guy was the winner. So on and so forth. Make sense? Finally, after we've asked those 6 questions, after temp is filled with the correct answers, let's see, correct vowels, copy its contents into pause. I want to kick that down a line. Well, we'll just do it on another line here. Put in positions left begin to right end. Copy them over into our original array. Okay? Now, the mechanics of this are not too difficult, but the number of things we had to keep track of to support these mechanics required us to draw some pictures, right? It's a lot of stuff for us to juggle. All right, so let's take this one step at a time in our solution. First thing we're going to need to do is we're going to have to create our temporary array of the correct size, right end minus left begin plus 1. So let's go back over to our code. So here's our merge sort. What did our merge sort do? It took in an array and then it made the appropriate call to merge sort helper so that the end user didn't have to come up with a 0 and ar.length minus 1. Merge sort helper went in and it did all the splits. It figured out left begin, left end, right begin, right end, and then called merge sort helper over and over again on the appropriate halves. After these 2 guys are done, and this is only in the situation when begin is not equal to end. If begin is equal to end, it's a 1 list. And by definition, 1 lists are sorted. So we don't need to do anything special, right? So our entire logic here lives inside of this if statement. We are only going to do something inside of merge sort helper if we have something bigger than a 1 list. And what are we going to do? We're going to figure out our 2 halves, the beginning and end of our 2 halves. We're going to call merge sort helper on each of those 2 halves. And then when we get to this line right here, when we return here, we have 2 partially sorted lists. Now we need to merge them together into a single list where all the values are sorted. Okay, I can tell you a little bit how to get started. So we're going to create a new array of the correct length and perform the merge algorithm, which we just went through, and fill that array with the correct data, then copy the contents of that array back over the original array from begin to end. All right, so what does our algorithm say to do? It says create a temporary array of the correct size. Right end minus left begin plus 1. So we're going to go ahead and we're going to create an integer array called temp, and this guy is going to be a new integer array of size right end minus left begin plus 1. So that guy will be the correct size. Okay, now we need to ask some questions. We need to create the vars for our 2 points, so the beginning of each of our lists. So we'll say cur left, cur right. So int cur left is equal to left begin. Int cur right is equal to right begin. So we've created 2 variables that allow us to keep track of our current competitor or current fighter in each of our 2 partially sorted lists. Okay? Then we're asking some questions. Temp.length number of questions. So we need to ask temp.length number of questions. So we're going to do something temp.length number of times. When we have to do something multiple times and we know how many times, what does that typically mean for us? For loop. For loops lend themselves to counting problems. So I'm going to do something temp.length number of times. So let's go ahead and do that inside of a loop. And it just so happens we were putting things inside of position temp pause. Right? This kept track of where we were inside of temp. So let's make our loop operate on temp pause. So we'll say for int temp pause is equal to 0. temp pause is less than temp.length, temp pause plus plus. Do we already have a temp pause somewhere? Oh, thank you. All right, so this loop's going to go take temp pause from 0 all the way up to, but not including temp.length, incrementing it each time. So this loop goes through every bucket of temp. Well, it takes temp pause on a voyage through all the indexes of temp. All right, so now inside here, we're going to ask some questions. These are the 6, well, in our case here, or by our example, our 6 questions we're going to ask. Now, the first thing we need to do is we need to find out if we're looking at any illegal combatants. Now, let me ask you this question. Is it possible for us to be inside this for loop and have both positions be illegal? Go back to our picture here. Is it possible for me to still be asking one of my 6 questions and to have cur left and cur right be illegal positions? It's not possible, because we are asking the exact correct number of questions, right? It's entirely possible that one of those guys becomes illegal. We might have a whole bunch of winners, maybe the first 3 times through, cur left wins. So from that point forward, the second 3 times through, cur left is illegal and cur right just wins by default. Okay? So it's entirely possible that one of them will be illegal. But it's impossible for both of them to be illegal at the same time. Okay? So if one of them is illegal, we're going to just pick the other one. If the other one's illegal, we'll pick this one. Otherwise, we have to compare. We have to duke it out. Okay? Have to fight. So we're going to ask the question, is cur left illegal? We decided that cur left is illegal if it's greater than left end. If cur left is greater than left end, then that means cur right will win. Correct? If that's the case, then what we're going to do is we're going to say temp at bucket temp pause is equal to AR, our original array, at bucket cur right. So cur right is the default winner if cur left is illegal, and then we'll increment cur right. We picked him as a winner, move him down the line. Okay? Else if cur right is greater than right end, that means left is the default winner, right? So temp at bucket temp pause is equal to AR at bucket cur left, and then we'll say cur left plus plus. Else. If we're in this else, what does that mean?
If nothing else works, then it defaults to L.
Well, what are the 2 things that already failed? Cur left is not illegal. Cur right is not illegal. So if we're inside this else, that means we're dealing with 2 legal positions. So we need to have them fight. We need to compare. Okay? So if we're inside this else, we need to find out who's bigger between those 2, because we know they're both pointing at legal positions inside of our sublists. So we'll say if AR at bucket cur left is less than AR at bucket cur right. If that's a true statement, that means the guy at cur left wins. So we'll say temp at bucket temp pause is equal to AR at bucket cur left, and then we'll say cur left plus plus. So if cur left wins, we do this. Otherwise, cur right must have won. So we'll say temp at bucket temp pause is equal to AR at position cur right, and then we'll say cur right plus plus. And we're going to do all of this stuff this many times. Okay? Just a bunch of questions. So we can see that in here, none of these questions are difficult questions. But it was still important that we drew those pictures so that we can make sure we ask the right questions in the right order. Make sense? So I think I've said it before, but I'll say it again. All hard programs are made up of a bunch of easy parts. When you just look at this for loop right here, there's nothing difficult about any of the code we've written there. Just a couple of arrays, a couple of variables, no big deal. Coming up with the right arrays and the right variables and the right positions and the right stuff, that's the more difficult part, right? But we don't need to solve that in syntax. We just wrote the syntax version of what we did over here. We solved it in pictures. Okay, and maybe you didn't squeeze everything onto one screen like I did here, but solve it on paper first, because any one of you could take two sublists like this and put them in order in a single list as a person, right? That's not difficult for a human being to do. If that was your final exam in here, if I gave you a couple of note cards and I say just put these in order, you'd all be thrilled. Okay, not a difficult task for us. What are we trying to do while we're learning to be programmers? We're trying to figure out how we actually think. How did we solve that problem? That's when we need to start drawing pictures. And what you'll find is you get better and better at drawing these pictures. You'll have to come back less often and add variables that you didn't remember before and things like that. So you need to go through this step of drawing pictures. Out of curiosity, those of you who worked on this assignment, how many of you drew pictures? 3 1/4 people? How many people got it done correctly? 2 1/4 people? By the way, those hands came from the same subgroup of those who drew pictures. So it wasn't necessarily trivial, but you certainly had a better chance of getting this right if you drew pictures. All right? So it's like programming plus art combined into one class. Right? You get to right? It's incredibly important. Every single one of you should be drawing pictures for every single one of your assignments. Remember a couple of classes ago when I had the brain fart with the pointers? It took a picture for me to understand what I did wrong. I was sitting at lunch with Josh Curcio, trying to, I think I told you, with the salt and pepper shakers. So we didn't have, those were our pictures. We were playing with our food. All right? So I still have to do it. Usually it's for more complex problems, but hey, sometimes you need to draw a picture to realize why you're being stupid. Make sense? So you all need to make a habit of doing this for every single assignment. You'll still find them hard, but you'll find them doable. If you're not drawing the pictures and you're just sitting here blankly staring at a wall of code, things are going to not go well for you. You're going to spend a lot of hours not getting very far. Okay? So this was not too bad if we already had this. If you were just staring at a blank wall here and saying, what line of Java do I write next? More difficult of a task. Okay? So, when we're done with this for loop, what is true? Temp is filled with the values from our 2 sublists in order. That's what's true. We have gone through every element from our left and right sublist and copied them into the appropriate places in temp. So at this point, after this for loop is done, temp has the exact stuff in the exact order that we want. Now we need to just copy it back into the appropriate positions in AR. Okay, that's what this last step does. It says, after temp is filled with the correct values, copy its contents. Put in positions left begin to right end, and here we'll say of AR. So we're going to have a loop that goes through AR from position left begin all the way up to and including position right end, because right end represents the last actual position in our right sublist, correct? Not one past it. It's the last actual position. So we need to write a loop that does that, and then we're going to need a secondary variable to keep track of the equivalent value inside of temp. Okay? So we'll go ahead and let's just create a variable here called pause. Int pause is equal to 0. So that's going to be our position in temp. In fact, let's go ahead and name it temp pause. And that variable is already out of scope because it lived and died with this for loop, right? So we can use it again. We can create a new version of that. So we'll set temp pause equal to 0. That's going to be, so the very first value from temp that we're going to grab is that position temp pause, which is 0. Then 1, then 2, then 3. But we're going to be taking that value, we're going to be copying it into position, in our case here, well, in our case here it'll be the same positions, but let's say we were doing our merge step when we were looking at just this list. We would have been copying bucket 0 into bucket 3, bucket 1 into bucket 4, bucket 2 into bucket 5. All right, because we're copying it into all the buckets of AR from left begin to right end. So we're going to create a loop for int I is equal to left begin. Keep going as long as I is less than or equal to right end I plus plus. So this loop is going to take us on a voyage through the legal positions in AR. Okay? And each time through, we're going to say AR at position I is equal to temp at position temp pause. And then we'll say temp pause plus plus. I is already incrementing. Now, you actually could have created both of these variables inside of a single for loop. I haven't shown that to you before, but you could have said int I is equal to left begin, comma, int temp pause is equal to 0. And then over here, we could have said I plus plus temp pause plus plus and gotten rid of that guy. Oh, it's not int there. It's like that. So, same ultimate logic, but I would say in general, I prefer that syntax. Let's just create the separate variable that we want rather than make our for loop look unnecessarily complex in this case. Okay? So, last part here, go through, copy everything back into AR. So now AR went from being 2 partially sorted sublists to be now 1 sorted list in the space of left begin to right end. And when are we doing this? We're doing it every single time that we return from our 2 recursive calls. So after we've gotten our left partially sorted sublist and our right partially sorted sublist, so the very first time we'll call this guy is when we get back 2 1 lists, or a 1 list and a 2 list, right? Something like that. Then we'll merge those guys together into a 3 list. Then that 3 list will come back, and maybe we have a 3 list and a 2 list. We'll merge those guys in together to a 5 list. 5 list, so on and so forth. All right, so we're doing this merge step every single time that we come back from calling merge sort. So we come back from calling merge sort when we have 2 1 lists, when we have 2 2 lists, we have 2 4 lists, so on and so forth. Till we all the way get back up to the top, in our case here, when after we did all the divide and conquers, all of these guys, and did merges at every step, we finally got back up here to when we had 2 3 lists in our current example and merged those together. Okay, so to test this, let's go ahead. We need to create a display method, right? So static void display, and this guy's going to take in an integer array as a parameter, and we're going to go ahead and spin through and print out the contents of that array. So let's go ahead and say for int I is equal to 0, I is less than ar.length, I plus plus. And I'm going to put a couple of asterisks before this and after this. Just to kind of block off our prints visually for us so we can keep them separate. All right. And then each time through, we're going to go ahead and we're going to say system.out.print. I'm just going to print them all on one line to keep the spacing for us. So we're going to say print AR at bucket I followed by a space. And then we'll do a system.out.println empty string. That'll kick it down a line. So what does display do? It shows some asterisks, kicks it down a line, goes through all the elements of AR, printing them with spaces between them all on one line. Then it kicks it down a line and puts 5 asterisks there. So we should see initially, when we call this, our unsorted data, then we'll call merge sort, then we'll see our sorted data. Is the way this is supposed to work. So we'll see if the moon's aligned for us. So here's our unsorted data by our current example. So we'll go ahead and say driver.display, and we'll pass it AR. Then we're going to call merge sort on that guy and let it do its magic. And then we'll call driver.display AR on the rest. Now I think right now, aren't we still printing some stuff in our merge sort, or did we take that out? No, we took it out. We're not printing anymore. Oh, and we already written a display down here, but whatever. That's just from begin to end. This will show us the final result. Seven, 8, 1, 3, 4, 2, 1, 2, 3, 4, 7, 8. So, and this was all the displays in the middle that we were calling. All right, so unsorted, sorted after our merge step. That make sense? All right, so questions about what we just did. So when you look at merge sort, let's go ahead and take out our wall of comments here. Shrink this down a little bit. The entire merge sort algorithm, when we deal with all of our spread out if statements here, is just this. Not that much code to pull that off. So a large chunk of the logic is built into these two calls, right? Because every single time we call merge sort, it's calling this entire function again. Passing in a different section of the list to focus on. We're passing around the same array over and over and over again. We're not passing around parts of the array. We're passing around the same array and then telling it which section of the array to look at using begin and end. Okay, so any questions on this? I would hope there would be at least some questions given that 2 people got it. Go ahead.
What does the plus after cur right and cur left do? Yeah.
Down here?
Yeah.
Okay, so this says if cur left is illegal, we're going to go ahead and declare cur right as the winner. And if we declare cur right as the winner, that means we need to increment cur right because the next time around, the next cur right's going to be the next guy. We don't want to keep taking the same cur right value over and over again.
Okay, so it moves like the...
Yeah, it's this guy.
Okay.
This guy right here. So cur right went from 3 to 4 to 5. So if we just declared 3 to be the winner, whether by default or he won the fight, we don't want cur right to point here anymore. We want it now to point to 5. So the next time around when we do this competition, we're comparing the value 4. Same thing's true over here. So whenever cur left or cur right is declared the winner, whether by default or by winning the fight, we're going to go ahead and we're going to have to increment them so the next time around we can compare the values. Okay, now had I already shown you GitHub in here? Okay, so this would be a good time for that. Because now we're starting to get into situations where having all of our code here would probably be beneficial for us to see. All right, so there is a tool out there called Git. Git. And this is something that's kind of standard across the software development industry. Git falls into the category of something called source control. So it keeps track of several things. It keeps track of all the changes, let's say all of the committed changes you have made to your software. And let's call this, it's ideal for collaboration between multiple developers. All right, so for example, when you guys work in groups, you should be, you could be using a tool like this, sharing your, well, I'm going to show you how to use GitHub, and I'll tell you the difference here in a second. Your link to GitHub saying, here's my current code. Can you tell me what's broken, or what am I doing stupid, or something like that, rather than copying and pasting chunks of code all over the place. You can just make sure your GitHub is updated and send them a link to it. All right. I'm also going to have you start submitting your code to me via GitHub. So rather than pasting your code in there now that our programs are getting bigger and bigger and bigger, you're instead just going to upload it to GitHub and just give me your link to that page for that assignment. So I can click on the link and go and look at the code. All right, so Git is a tool for source control, keeping all the copies, all the changes you've ever made to your code. Yeah.
Can you, if you're looking at somebody else's code, can you edit it, or is it read only?
Read only. You can do what's called fork their repository, so you get a copy of it, and then you can work with your own version of it, and you can edit that. But you can't, if you give somebody the link, they can't break your project. If that's what you're asking. They can't destroy your code. They can make a copy of it and destroy their own copy, but they can't mess up your code. So now there's two tools that we're looking at here. So one is Git. The other one is GitHub. GitHub is a website that acts as a remote Git repository. All right, that's what GitHub is. So when we use Git and GitHub, what we'll be doing is we'll locally be creating a Git repository. So inside of our directory where our Java files live, we'll create a local Git repository. Then when we're ready to actually, so we'll make changes, we'll commit them to our local Git repository, whatever. All that's happening locally on our machine, not connected to the internet, all that jazz. Only when we want to share it with the rest of the world, or back it up to the cloud, so in case something happens to our computer, it's saved. And by the way, hopefully everybody in here is using Dropbox. If you're not using Dropbox, you should be using Dropbox, and you should be doing all your programming inside of Dropbox. Okay, because I'll just laugh at you if you ever come to me and say, oh, my dog ate my homework, the equivalent of the, oh, my computer hard drive crashed and I've lost all my code. Well, that should never happen to technologists, because our code should always be backed up in the cloud. And since we're all probably too lazy to manually back it up in the cloud, Dropbox is awesome because you just work in that folder and it automatically backs up in the cloud. You don't have to do squat. When something bad happens, you just magically go, whew, it was up there. Thanks. All right. So if you're not using Dropbox, you didn't want to raise your hand and admit it, use Dropbox. And use one of the links in general on Slack, so the computer science, well, I think it's Concordia as a whole, gets credit for, because I think right now, if you sign up for Dropbox under a CUW account, I think instead of 2 gigabytes free, you get 5 gigabytes free. I think we've won 3 gigabytes. I think that's right. So quite a bit of storage without you having to spend a dime. Okay. So GitHub is a website that acts as a remote repository. Git is the actual technology. It's the actual tool that we'll use to create a local repository. So in the end, you'll actually have 2 copies of your code. Well, 3 copies of your code. Well, if you're using Dropbox, 4 copies of your code. 1 copy lives in your hard drive. Another copy lives in your Git repository on your hard drive. Another copy lives in Dropbox. Technically, you have a copy of your Git repository on Dropbox as well, so 5 places. Okay, and then you'll also be pushing to GitHub whenever you need to share code with somebody or submit your assignments or something like that. Okay, so we're going to go through that whole process right now. So what I'm going to do to start with is we're going to go ahead and we're going to go to the, here we go, I've got GitHub up here. So as an example, here's our repository we're using for the operating systems class. We're writing an operating system simulator in there. So here's our PCB class. So this is what I would look at when you submit your homework. I would see all your individual files. I can click on any one of them and see the code and all that jazz. Okay, so this is what it would ultimately look like to me. So this is from our original commit, and then as we've added stuff from class, we've pushed updates, and now we have added stuff. So what I'm going to do is go to, it's github.com. So once you go to github.com, you can go ahead and create an account on here and that kind of stuff. Once you have your account, you hit the little plus sign here. We're going to create a new repository. Now GitHub is free. as long as you're willing to have all your code be publicly available to the world. If you are an organization, GitHub's kind of an industry standard tool. Most development places will use GitHub. So it's a good tool to learn if you're going to get into an internship or something like that. It's going to be a resume pattern that you already are familiar with this technology. But if you're working for a place that's working on a video game or a business application or something like that, something that's not necessarily for public eyes, they're probably paying the GitHub fee to have private repositories. So they can have their stuff up here for collaboration amongst their employees, but not for the whole world to steal their code. All right? But all you should set up a free one. So we're going to call this CSC250 Fall 2015 mergesort. That's going to be the name of this repository. All right, and it's going to be public. And I'm just going to go ahead and say commit or create repository. And the very first page it gives me is essentially the list of instructions that I have to type in. Now, there are some plugins for Eclipse that allow you to use GitHub through Eclipse, and they suck. Okay, so I would not recommend you do it. In fact, from my experience, the only acceptable, well, there's two. The two acceptable Git compliant tools for graphical IDEs is the one for Xcode, which is really good. And that's for the Mac if we're doing iOS development, stuff like that. And also the one for Visual Studio. Although Visual Studio, they actually want you to use Microsoft Source Control. It's like a competitor to Git, but it works well as well. But this is the way that will always work. Okay, no matter what kind of thing you're doing. If you're working, you can save term papers this way if you'd like. GitHub's kind of designed for programming changes, so you can see if 5 different developers are working on the same product. You can see who made what change last, who broke something. That kind of stuff, or maybe you can actually branch an application. So you have your master branch, maybe that's the released version of the software. And then you have the beta branch, that's version 2 that they're currently working on. So you can commit changes to the beta branch without breaking the master branch, that's your current software you've released. And then at some point after you've tested the beta branch, maybe you shift that over, that becomes the new master branch. Kind of makes sense. So it's a tool that's kind of a power tool for that. We're not going to be using it for all those features. We're basically using it to back up our code and submit it as homework. Okay? But it's also going to be a good way for me to put the code up and then share it with you. All right? So it gives us the instructions we need. Now, if you're on a Mac, Macs already have Git installed on them. Okay, they already have Git installed on them. I'll show that to you here in a second. If you're on a PC, you'll have to go and get the Git for Windows. That's this guy right here. And ultimately what it's going to give you is after you finish downloading it, you're going to be doing the exact same thing that I'm looking at here on the Mac. When you double click on it, it's going to open up a terminal-like window, something that looks kind of like DOS, but it's not DOS. All right, it's the Git shell, if you will. Okay, so here I'll paste this on. There's the Git for Windows link in the 250 channel. Okay, and then once you have that installed, you can follow the exact instructions we're doing here. Okay, so every time you create a new repository, it actually gives you the starting stuff you need to do. All right, but whenever you do this stuff, you need to make sure that you're currently sitting in the same directory where your code lives. So I'm going to go ahead and I'm going to open up a terminal. So this will be equivalent to what you'll see when you, if you're on a Windows machine, when you double click on the Git program. And I need to get to the place where my code lives. So I actually keep my code on Dropbox. So go in here. So inside of our, didn't we call this merge something? Oh, that's right, that's right. We didn't call it mergesort. So here's our dice roller. Here's our source. So really it's just in driver here, right? All right, so I'm actually going to put all this code up here so you'll have it because it'll be easiest to do it with all these files. All right, so I want to get to where this source folder is. So I'm just going to go ahead and drag the source folder over here. So on a Mac, I already typed CD in, and then this gives me the full path to where that is. If you're on a PC, you'll have to type in cd and then put in the path wherever your directory is. So that when you press enter here, if you type in, once you have that terminal on your PC, you'll have a command called ls, which is equivalent to dir. Okay, it's the directory listing. So ls shows me everything that's in that directory. I should see my files that I ultimately want to put on GitHub here. Make sense? All right. So my present working directory is this guy. It's on my Dropbox. All right. So very first thing I do, go back here to the website. We do git init. So that initializes a Git repository in that directory. Git init. So it does some sort of magical crap. When I type ls, something doesn't seem like it's changed, but if I type ls-a, I see I have a new folder here called .git. So any folder that has a dot in front of it, by default, is a hidden folder. Okay, so it's created a local repository for me with nothing in it called .git. And all I did is I had to create that by saying git init in this directory. You only have to do that once per repository, okay, per project you're working on. Now, if you follow all the directions here on the GitHub site, the next thing they tell you to do is add a README file and that kind of stuff. I don't do the README thing. So this is like you creating a repository before you have code. We already have our code, so I skip this line. So let me just do what I usually do. So I want to add all of my .java files to this repository. So I'm going to say git add star.java. Okay. For those of you who are in the iPhone or the Apple Watch class, we actually use Xcode to do this, and it adds your whole project up there. For us, we're just going to add the .java files. So if you need to add things other than just .java files, you just say add star. All right. We're going to say star.java. So that just added all the .java files to our repository. Okay. Now if I do a git status, I see that here's all the files in my repository, and they all show up as new files. That is, these are files I've added to the repository that aren't currently already in the repository. Okay. Now, if I decide I've made my changes, the current state of my application is stable, and I want to kind of take a snapshot of this. I want to commit it to the repository. I'll do a git commit -m for a message, and let's just call this initial commit. Okay, so I'll go ahead and do that. So now it tells me it's created some files in there, and it's done 4 files changed, 254 insertions, whatever, blah, blah, blah. Okay, so now those things are changed. If I do a git status now, I see that nothing has changed. My local code is equivalent to my repository. Those two guys match each other right now. Okay, so as far as Git is concerned, I just finished committing a project to a Git repository. But it's not in GitHub yet. So Git is the actual tool. GitHub just happens to be a Git technology compatible website. So that's where I need to go back to GitHub, and we have this line right here. Git remote add. So I can tell Git about my GitHub repository. So I'll actually just copy this line, because this actually gives me the full path, the web path of where my actual mergesort Git lives. Okay, so I'll go ahead and paste that in there. So now I've added a local variable to this particular Git repository, letting it know that I have a remote repository whose name is origin, whose position is, whose location is that. I only have to do that once. Okay? So from this point forward, as long as I'm working with this particular repository, it already knows about my remote place. So I can commit locally, and that doesn't affect the remote one. But when I want it to go to the remote place, I have to do a push. That's this line right here. Git push -u origin master. So I'm calling the git command. I'm doing a push. Here's the name of the remote that I'm pushing it to, and I'm pushing the master branch, which is the default branch they provide for you. Hit enter, and it goes ahead and does its magic. The first time you do this on your computers, it will ask you for your GitHub username and password, but it will remember that from that point forward. So I've done this before, that's why it didn't ask me for it. Okay, so now it's up on GitHub. So if I come back here and I click on this, you see my code's there. Okay, so here's our driver that we just wrote. Here's all of our merge sort code. And then as an example of how this can kind of work, I'll go ahead and let's just go into our, let's just add a couple of comments in here. Well, here, let's actually just, let's use the random class and generate a random array. So we'll import Java, well, we'll let it do it for us. We'll let it import java.util. So we'll say random r is equal to new random. And then we're going to say, let's go ahead and import here. AR is going to be a new integer array of size, let's just make it 10. For its I is equal to 0, I is less than AR.length, I plus plus. We're going to go ahead and we're going to say AR at bucket I is equal to R dot next int, let's say 50. That'll give us numbers between 0 and 49. Then we'll go ahead and we'll display the 10 values, merge them and display them again. And let me go ahead and take out our display right here. That was all that extra crap that was being thrown in there. Here's the unsorted, here's the sorted. All right, so we've made some changes to our code now. All right, so if I go back out here to GitHub, I'll go ahead and do a git add, or to the Git repository. I'll do a git add star.java, then I'm going to do a git status. Okay, and we see that out of all those files, one file was actually modified, driver.java. Okay, so now I'm going to go ahead and do a git commit -m, filled a random array to be sorted. We'll commit that, and then we'll do a push. So now it's up on GitHub. So I come back here to GitHub. We see that we filled a random array to be sorted. This guy was just changed up here. So if I click on this file, I see what's changed. Here's the old version. Here's the new version. Okay, so we can see the modifications we've made from the multiple versions of our code. Kind of makes sense how GitHub works? Okay, so your homework for next class is to take your current code, bring it up to snuff, so get your merge sort working. And I'll give you, you have access to it now. I'll go ahead and give you the link to the GitHub repository. So there's the GitHub repository. So you have the code now. Okay, so go ahead and fix your code, get it working, create a GitHub account, create a repository, upload it to the repository, and submit your link to it. Essentially proving that you now know how to use GitHub. Make sense? And for all I care, I mean, I would suggest you try to update your code, but realistically, if you just want to copy my code, I'm fine with that. I'm not going to look at the code. I care more about you being able to put the stuff on GitHub. Make sense? All right. I'll go ahead and I'll put that up on Blackboard now. I'll let you out a couple minutes early. Remember, we have the computer science get-together, so go to the bathroom, put your bags away, whatever you need to do, but make sure you get down there relatively quickly so you're there for the very beginning of the little meet and greet thing we do, because whoever wins that, I think the top 2 people, they get first dibs on the prizes. So you'll get first dibs on the good prizes rather than have to deal with the crap. Okay? So right down the hall in S118 is where we'll meet here in 15 minutes, but get there as soon as you can.